For any help regarding solid mechanics assignment help, visit https://solidworksassignmenthelp.com/. Email info@solidworksassignmenthelp.com or call us at +16786484277. solidworksassignmenthelp.com. Problem 1. A cantilever beam has been constructed from a steel having Young's modulus E is equal to 208 GPa, Poisson ratio Nu is equal to 0.29, and tensile yield strength sigma Y is equal to 410 MPa. The length of the beam, from its base to its tip, is L is equal to 1 meter, and the uniform cross-section is rectangular, H is equal to 5 millimeters thick, and B is equal to 30 wide. Two axially mounted strain gauges have been mounted on the top surface. Y is equal to H/2. The precise absolute axial position X is not known for either gauge. However, it is known that the two gauges are spaced an axial distance of L is equal to 200 mm apart along the length of the beam. A tip load of magnitude P is applied to the cantilever, acting in a direction parallel to the y-axis, causing the two gauges, number 1 which is nearer the base of the cantilever, and number 2 which is nearer its tip, to register the following strain values. solidworksassignmenthelp.com. Figure 1. Schematic of tip-loaded cantilever showing positions of strain gauges numbers 1 and 2. Times evaluate the load P. Times using the known value of P, find the axial locations x1 and x2 of both gauges. Problem 2. There is current interest in the use of microfabricated cantilever beams in detecting the presence of bacteria in a liquid solution. Following fabrication of the cantilever, its surface is coated with an antibody that is specific to the presence of the bacterium of interest, and the free vibration characteristics of the cantilever, its first mode natural frequency, ω0, is recorded experimentally. solidworksassignmenthelp.com. Then the coated cantilever is exposed to a liquid medium. If the sought-for bacteria are present in solution, they will preferentially attach themselves to the antibody coating on the surface of the cantilever, in the process increasing the vibrating mass of the cantilever by an amount delta m is equal to NB/MB, where NB is the number of bacterium cells that attach, and MB is the mass of the bacterium cell. Figure 2. Scanning electron microscope images of E. coli bacteria attached to various microfabricated resonating cantilever beams. From Illich, et al., Applied Physics Letters, 77, number 3 2000, 450452. Subsequent testing of the added mass cantilever should reveal a progressively decreasing natural frequency as more bacterium cells are added. The cantilever of interest has been fabricated of silicon nitride, having a mass density of ρ is equal to 3.1 times 103 kilograms per cubic meter, and Young's modulus of E is equal to 100 GPa. It has a uniform rectangular cross-section of thickness H is equal to 320 nanometers, width B is equal to 15 m, and total length L is equal to 100 m. Times assuming that the antibody coating itself does not appreciably affect the natural frequency of the cantilever, estimate the first mode natural frequency, ω0, of the cantilever. solidworksassignmenthelp.com. In the absence of adhered bacteria. Note, please refer to the Lab 1 handout notes on vibration of cantilever beams for relevant analysis. Times assume that the added mass delta m is equal to NB/MB is uniformly distributed along the length of the beam, and further, assume that the presence of the adhered bacteria does not affect the stiffness of the beam. Let the total mass of the coated beam be m is equal to ρBHL, assuming that show that the change in frequency resulting from the added mass, delta omega, can be expressed by. Hint number 1. You might wish to show that the natural frequency of a uniform beam of total mass m can be written as, neglecting dimensionless factors. Hint number 2. If the change in total resulting frequency of the perturbed mass system can be evaluated by taking a tails, delta m, is very small in comparison to the initial beam mass, m, then the OR series expansion of the frequency expression about the reference mass. SolidWorks assignment help.com. Times assume that the cantilever has been covered by Nb is equal to 100 bacterium cells. From the figures, it appears that the diameter, dB, of each bacterium cell is near dB is equal to 1 m, assuming each cell to be spherical and to have a mass density, ρb, equal to that of water. Justify an estimate of each cell's mass as Mb is equal to 5.24 times 1016 kg. Using this estimate, and assuming that the cell added mass is uniformly distributed over the surface of the beam, evaluate the change in natural frequency that you can expect to see for the bacterium-coated cantilever. Problem 3. Atomic force microscopy resolves the structure of surfaces to near atomic level resolution. A key structural element of an atomic force microscope, AFM, is a small cantilevered beam fabricated from a material such as silicon using lithographic technology, example, precision etching. The beam has a sharp-tipped diamond stylus at its tip. The stylus is tracked across the specimen surface, and very local surface interactions between the tip and the specimen surface cause the tip of the cantilever to deflect. The magnitude of the tip deflection is measured by reflecting a laser beam of its backside and imaging the location of the reflected light. The tip surface forces are computed from the deflections using beam theory, and they are used to map the structure of the surface. Figure 3 shows a small rectangular cross-section cantilever from an atomic force microscope, AFM, that has been machined from a single block of silicon using lithographic technology, example, precision etching. The nominal dimensions of this cantilever are length L is equal to 460 m, width W is equal to 50 m, and thickness T is equal to 2.0 m. Elastic constants of silicon are Young's modulus E is equal to 107 GPa, and Poisson ratio Nu is equal to 0.2. SolidWorks assignment help.com. The stiffness K is equal to P delta of the AFM cantilever is an important design parameter. Times compute the stiffness of this AFM cantilever. Times unfortunately, dimensional tolerances in the etching technique inevitably lead to a range of dimensions over a population of the AFM cantilever products. The manufacturer quotes the following tolerances for this cantilever: L is equal to 460 m plus or minus 5 m, W is equal to 50 m plus or minus 3 m, and min is equal to 1.5 m less than or equal to T less than or equal to TMAX is equal to 2.5 m. Accordingly, the stiffness of any given cantilever can vary from its nominal value, depending on its actual dimensions. Provide estimates of the minimum and maximum stiffnesses, KMIN and KMAX, that can be expected is this cantilever, corresponding to extreme ranges of the dimensions. Problem 4. CDL Problem 8.15. Hint suggestion, Problem 8.15 is the continuation of the self-weight cantilever problem we looked at in the lecture. You should be well on the way to solving for its moment distribution, and then you should be able to follow the procedures adopted for the tip-loaded cantilever to calculate the corresponding lateral displacement distribution, V, kiss smiley, and anything else needed. SolidWorks assignment help.com. Problem 8.15b is statically indeterminate, meaning that there is no direct way to evaluate its bending moment distribution M. Kiss smiley without